This shows the success of this model. At least it can be used in the field, first through a clinical evaluation, and then full-scale deployment, essentially to be finally a triage tool where it performs the screening process alongside radiologists, but with a full-scale deployment. These are some of the sources. I would especially like to acknowledge the Makerere University Research and Innovations Fund that has been able to grant us funding for this project through the government of Uganda. We thank you for that, and with that, good evening, good afternoon. Yeah.
Okay, thank you very much. Thank you, Philip, for your presentation. I will have the discussion afterwards. Yeah, thank you. We're going to have our next presenter, Brenda Birungi. She's going to talk about automated recognition of lesions suspicious of breast cancer in ultrasound images. To the rest of the presenters, please be mindful of that time. We have 10 minutes each. Brenda, you're welcome.
My name is Bashimera Brenda Birungi, and I am a student at Makerere University, pursuing a master's in computer science, majoring in artificial intelligence and data science. Our research is a deep learning approach for breast cancer diagnosis in breast ultrasound images and under the supervision of Dr. Joyce Nakatumba Nabende, Dr. Cosmas Mwikirize, Richard Malumba, Dr. Andrew Katumba, and Professor Michael Kawoya, in collaboration with the AI lab of Makerere, Makoni Lab, Akure, and Makerere University. Breast cancer is a leading cause of cancer mortality worldwide, and when we look at our graph on the right, which information was collected by the International Agency for Research on Cancer in 2020, we see that amongst all other cancers, breast cancer has the leading incidence rates, and and it comes after lung cancer with the highest mortality worldwide. Specifically in Uganda, which is one of the countries in the sub-Saharan region, breast cancer has an age-standardized incidence of 21.3 for every 100,000 new cases, and an age-standardized mortality of 10.3 for every 100,000 new cases. And this high incidence is largely attributed to scarcity of readily available breast cancer screening and education, and a diagnosis that typically comes late. And we see that when there is late diagnosis of breast cancer, this negatively impacts survival. So in the global context, we have quite a number of screening modalities of breast cancer, which include the use of MRIs, mammographies, and ultrasounds. But in Uganda specifically, there is a wide adoption of the use of breast ultrasounds because they're cheap, they're highly available. Breast ultrasounds are non-invasive and provide real-time capabilities. We have looked at all those advantages of the use of breast ultrasounds, but there are also challenges that come with the adoption of the use of breast ultrasound imaging, and one of the commonest challenges is the high rates of false positives. So when we have high rates of false positives in breast ultrasound images, this will lead to recommendations of biopsies for patients, and in most cases, when these biopsies are recommended to be taken by the patients, still research has been done that the false positives that also come out of the biopsies that are made are up to 71%, and this research was made in the United States in 2021. So we realized that the diagnosis or the interpretation of breast cancer from breast ultrasound images is largely attributed to the experience of the radiologist at hand and the radiologist's level of judgment. Reason being, when these breast ultrasound images are interpreted, there are a number of factors that need to be put into consideration before making conclusions from the ultrasound images. And some of these factors include posterior acoustic shadowing, we have enhancement, we have how the edges on the lesions look like, we have lobulation age. So this in order to help the radiologist make accurate conclusions from the breast ultrasound images, a lot of work has been done around the automation of breast cancer diagnosis. Literature shows that a lot of work has been done in fields of machine learning, specifically segmentation, classification, and detection. But where is our problem? We have seen that a lot of work that has been done using segmentation, there is a disadvantage that comes with the use of segmentation, whereby segmentation has insufficient sensitivity and specificity because it limits its region of interest to the lesion itself. When we look at the image that is below there, we have a breast ultrasound image of before segmentation, and when we look at after segmentation, we only see that it's the lesion that has been segmented in the color red, putting other factors constant that are specific to this lesion. We also get to realize that breast cancer affects different populations differently. So in order to come up with a model that generalizes well with a specific population, there should be an authentic representation of the training data given to the model, thereby creating a need to develop a more generalized model for the detection of breast cancer, whereby the labels that are incorporated into the training data put into consideration all the artifacts that affect breast, all the artifacts that come along with a diagnosis of breast cancer. So our aim is to develop a deep learning model that is aware of the morphology of the breast ultrasounds and differentiates between the suspicious and non-suspicious breast lesions using ultrasound images that are acquired from sub-Saharan Africa. In our methodology, before training our model, we acquired 3 sets of data. The data that was acquired from Makerere, we made an ethics clearance application to Makerere and Uganda National Council of Science and Technology to be able to acquire the data set from Makerere. And we also acquired 2 other data sets, one from Cairo University, which is an online domain, and this data set can be accessed by anyone, and the data set from breast and axilla. When we look at the images from our left, before please, the prior slide. Yes. When we look at these images on the left, some of these images were acquired from the Cairo University, and the images were completely labeled with their classes of a range from BIRADS 1 to BIRADS 4, and all of these images came with their corresponding masks, which helped us in the process of data labeling, like we shall mention later. And the images from breast and axilla did not contain their corresponding masks, as well as the data from Makerere. So after acquiring the images, we went through a series of discarding insufficient. Next slide, please. We went through the process of discarding insufficient and incorrect data in our process of data cleaning, and after we had discarded this incorrect data, the data that was left, we used in painting to remove the unnecessary markings, as we see from the first image 4, because these markings were not required as our end result after model testing. So after using in painting, this is the image on the left. The second image is what we acquired. After data cleaning, we went through a series of data labeling with the help of radiologists from Makerere and Professor Michael Kawoya to provide the labels to the data of suspicious and unsuspicious. And after data labeling, we did data augmentation, because when we look at the data sets that we acquired, more data belong to the non-suspicious class than the suspicious class. So in order to provide a certain form of balance, we used horizontal flipping to generate more breast ultrasound images. After the process of data pre-processing, we used YOLO version 4 as our baseline architecture. And this model took in, we provided the images to this model, and the model resized the images to 416 by 416. Then the model learned the features from the breast ultrasounds automatically, and then the end result was bounding boxes together with the classes that attached to each image. So for our training process, we trained our model, the YOLO version 4 tiny model, in 3 phases, depending on the data set that we used in the training process. For phase 1, the model was trained on only public images. Phase 2, the model was trained on only images from Makerere, and for phase 3, the model was trained on a mixed data set, which included both images from the public domain and Makerere. Once we tested, the testing was done on only images from Makerere. And in phase 1, there was an training test split of 80 to 20, as well as phase 2. But for phase 3, we used all the images from the public data set and 131 images from Makerere, and then for testing, we used 83 images. For our comparative analysis, we looked at other algorithms for classification and detection to benchmark which one would provide the best solution for our problem compared to the YOLO V4 Tiny approach. And those models were support vector machines, VGG16 and k-nearest neighbor for classification and efficient date as the other object detection algorithm. So our results after testing all the 3 models that we trained in the 3 phases on only images from Makerere, we see there is poor performance once we do not provide part of the data set in the training that belongs, that comes from the sub-Saharan region. So when we tested Makerere images on the model trained on only public data, we see that we got a precision of 0.77, a recall of 0.1, and an accuracy of 2%. The F1 score improved once we only tested the data set on only images. When we trained the data set on only images acquired from Makerere and tested on them as well, we see an improvement in accuracy of 52%. And we see a vast improvement in the performance once we provide the training set with part of the data that we use. Once we provide part of the training set with images that were acquired from Makerere, we see a performance of 89%, which validates the fact that for a model to generalize well for a certain population, for example, here in Uganda, we should provide the model with an authentic representation of the images where the population lies for training. Some of, next slide please. We might not see this clearly, but the markings that are in purple are those of the non-suspicious predicted class, those that are in the first row, and the second predictions are that from the suspicious class. And we see that our model did a good job at incorporating all the artifacts that are specific to the breast lesion, and the detection was not tied to the lesion itself. When we did testing on other algorithms, we acquired, next slide please. We acquired an sorry, I think there's an error on that slide. We acquired an accuracy of 0.816 for support vector machines, 0.864 for K-nearest neighbor, 0.67 for VGG16, 0.69 for efficient det, and 0.89 is the value for the YOLO V4 tiny model. So this shows us that a detection solution was the best for this research, and YOLO V4 tiny provided us the best results. Next slide, please. Yes, we had some limitations to our work, and the major limitation was still having an imbalanced data set. Even though we had performed some image augmentation on the images, there was still more non-suspicious images by 21.2% from the suspicious images. And we also had less images that were coming from Makerere, which we used as our retrospective data from Makerere. And also, earlier, Professor Kawoya talked about the doctor-patient confidentiality of the images that we were given. Yes, the images were labeled, but we were not sure whether these images really came from patients that are from sub-Saharan Africa. So that was one of our limitations. In the future, we hope to expand on the size, diversity, and the balance of the data set, especially the images coming from Makerere, and we hope to integrate the developed object detection model into our clinical workflow. Next slide, please. We thank the supervisors to this research, Dr. Joyce Nakatumba, Nabende, Dr. Cosmas Makerere, and Dr. Andrew Katumba. We also extend a deep thanks to Professor Michael Kawoya and Richard Malumba from Makerere, and also the funders of this work, which was the Carnegie Corporation of New York. Thank you. I submit.
Thank you. Thank you, Brenda, for your presentation on breast cancer diagnosis in ultrasound images. Our next presenter is Ben Mugalu. Ben. Ben is going to talk about a computer-aided diagnosis system for cervical cancer from colposcopic images. This work is jointly done with the Uganda Cancer Institute. Brenda, Ben, you're welcome.
Thank you, Dr. Joyce. Good afternoon. My name is Ben Wycliffe Mogalu. I'm a research assistant at the Makoni Machine Learning Lab. I'm going to be sharing the work we've done in the development of a computer-aided diagnosis system for cervical cancer from colposcopic images. Cervical cancer is one of the most common cancers in women and a major public health problem affecting middle-aged women, most especially in less privileged countries. Now, according to the World Health Organization, a survey was made in 2018, and it concluded that there were approximately 570,000 cases of cervical cancer, of which 311,000 were deaths. It is one of the most dangerous cancers affecting women, and research shows that the mortality rate due to it is 90% in the less privileged countries. The good news is that it can be treated if diagnosis is done at a much earlier stage, when the precancerous lesions are just developing. But the challenge is that there are not many economical solutions out there for the diagnosis to sustain this activity in the less privileged countries. Some of the methods of screening that are popular include the testing of a human papillomavirus, which is directly responsible for the development of cervical cancer lesions, and the pap smear test, which is a cytology-based method for diagnosing cervical cancer. But the challenge with these methods of screening is that they are relatively expensive and they require highly trained personnel, radiologists, which we do not have to sustain the low privileged countries. Another popular method is visual inspection with acetic acid. So this involves a radiologist or an expert directly looking at the cervix and determining whether there are existing precancerous lesions. Research shows that VIA has a higher sensitivity compared to the testing of the human papillomavirus and the pap smear test, but it has a disadvantage that it has a limited accuracy. Though on top of having a higher sensitivity, it's also easier to work with, so that means less experienced personnel can work with this, and it's also very cheap compared to the others. The other disadvantage with VIA is that it's highly subjective, so the VIA result is much dependent on the person doing the diagnosis through VIA. Now, VIA has 3 approaches. The first approach involves inspecting the cervix with a naked eye. The other approach is through a colposcope, which is a device, and this comes to help with the problem encountered with the first approach, which is the naked eye inspection. So the colposcope gives the person inspecting the cervix a better view of the cervix. Though it helps with the first approach, it also has a disadvantage that is quite cumbersome and a bulky device. So that's where the mobile colposcope comes in. Essentially, you have a smartphone mounted on a ginocular. So this is an easy way to perform VIA. It's called the mobile colposcope, and this is what we work with in our approach. Researchers have done several studies and suggested approaches that utilize deep learning to try and improve the accuracy of VIA, which is the major disadvantage here. On the screen, we have an architecture of one of the methods that was suggested. This relies on multiple inputs, and these include colposcopy images. One is stained with acetic acid, the other is stained with iodine. And we also have a number of structured variables, inputs. So these extract features from the images and the variables and then concatenates them to perform a classification. So with this, they managed to achieve an accuracy of 85%. And a recall of 85% and an accuracy of 84%. Another method suggested by researchers, they came up with a custom architecture which they call the corponet, and this also takes in a single colposcopy image and then performs a classification on that. With that, they managed to achieve an accuracy of 81.353%. So why we're doing this? Much as we've seen that there are efforts made to try and eliminate this problem, they still need to improve the accuracy with VIA. We've seen that one of the best performing architectures was relying on a lot more data. So that means that will be a very expensive architecture to deploy through maybe a mobile application. So what we're trying to do is develop a high performing classifier based on deep learning that classifies that bases on just a colposcopy image to determine the existence of any precancerous lesions for cervical cancer. Good. So our dataset was acquired through a clinical study that was approved by Uganda Cancer Institute Research and Ethics Committee. This was conducted at various locations, which included Arua, Mayuge, Mbaro, and Kampala. And our primary data collection tool was the ODK application. So through this, we captured a number of form instances. And a form instance came with a number of other attributes, most of which are kept confidential. And for every form instance, we captured 2 to 4 images, where half of these images were taken before staining the cervix with acetic acid, and 4 of the images were taken, rather, the other half was taken after staining the cervix with acetic acid. During data collection, 3 parties were involved in the VIA process. So there was a nurse taking an image and a nurse taking a VIA. But when it came to the VIA decisions, both parties were involved. And whenever they were not sure, they involved a gynecologist to make a final decision on what the VIA result is. So that means that the VIA results we got from the field had 3 parties involved. So being aware of the challenge of bias when it comes to the VIA assessment, we wanted to conduct an experiment that compares VIA results from the different experts that were involved in the whole clinical study. So we developed an annotation tool, and through this, we established 2 groups of nurses and also created a gynecologist account and had all of them annotate the same data set. So we had 3 different labels for the same patient cases. So through this tool, we captured the VIA assessments and a number of other attributes, including comments and bounding boxes around the cervical areas, just for development, the diversification of the data set for other applications. So when we conducted the reliability assessment of the results that we got by establishing the groups of nurses, that's group 1 and group 2, and the gynecologist. So we compared all the annotations, and our metric was the Krippendorf's alpha reliability. Now with the Krippendorf alpha, the threshold for a reliable for reliable annotations is 0.67, but you can see that for all of the comparisons we've made, the score is relatively low, so that means the labels were not reliable due to the bias. Like it wasn't reliable taking specific labels from one nurse group or the gynecologist alone. So with that, we settled with the labels that came in from VIA, which involved 3 parties. Then we went ahead to partition our data set for classification, with the target variable being the VIA results from the field, not the VIA results we generated through the annotation tool. So this is what our data partitions look like. So we went ahead and augmented our data set since we had a relatively small number of images, and the way we chose these augmentations was in such a way that we maintained the intrinsic features of the images. Next slide. So our architecture is based on the VGG19 state-of-the-art model that was pre-trained on the ImageNet. So on top of that, we maintain the pre-trained weights for the first 4 convolution blocks and unfroze the rest of the convolution blocks together with our artificial neural network. So through this, we made a number of iterations and continue. Yeah, so these were the results from the base model. So we managed to achieve 97% sensitivity, which implies that for every 100 positive images, we would detect 97 of these. We had a relatively lower specificity, but our interest was in the sensitivity metric, since this is a sensitive diagnosis we're trying to make, and we are very much interested in determining any